Hi, welcome back to Mrs. Thompson's classroom today. We're going to be talking about Riemann sums. Riemann sums are a way to find the area between a curve and the x-axis. And so we're going to use rectangles to estimate our area. And of course, the more rectangles we make, the better estimate we get. And there are a few different ways of doing this depending on how we choose to make our rectangles, either from left or right or the midpoints. There are actually ways to do this using trapezoids, which get us a little more accurate. So let's get started by just looking at a example with the function 8 minus 1/2 x squared. So it's a parabola, and we're going to find the area between the curve and the x-axis from x equals 0 to 4. So that's this shaded region. And we're going to estimate it using 8 sub-intervals. So that means we're going to make 8 little rectangles. So the first thing we need to do is we need to divide our piece into these sub-intervals. So we're going to find our change in x. So if I want to draw one rectangle from here to here, this distance right here is my delta x. Okay? So if I want 8 sub-intervals, we're going to take the length of the interval and divide by 8. So that gives us 1/2. And then I form my partition by calculating what those values would be by adding a 1/2. So I'll get to a 1/2, and then I add a 1/2 again, and I get to 1, and I add a 1/2 again, and I get to 1.5. And then I add it again, and I get to 2, and so on until we hit the end of our interval, which is at 4. Now notice to make 8 sub-intervals, you will have 9 numbers in your list. Keep that in mind. All right, so here's the picture using left endpoints. So the left endpoints will start at 0, but they're only going to go to the 3.5 or 7/2. Because that right here is forming this last rectangle, because I'm going to use the left-hand side. So I will not use the 4 if I'm going from the left, okay? The area of each rectangle is going to be its length times its width. So the width is this delta x down here. The height of the rectangle is the function value itself, right? So the rectangle 1 is going to be f of 0 times our width, which is a 1/2. And then rectangle 2 is going to move to the next endpoint and do f of 1/2 times the delta x, which is a 1/2. And we're going to keep calculating these. So you can pause the video for a minute and see if you can calculate each of these yourself. You're going to end up with 8 rectangles. So go ahead and pause it and see if you can calculate them. All right, so here they are, all 8. Okay. Notice the last one is at that 3.5 or 7/2. Okay. Now to get the estimate for the entire area of this region, we're going to add all those together. So we just add them up and we get 23.25. Okay. Now, if you're using a graphing calculator, there are nice ways to do some of this work for you, and I may make another video on that. But you can put your function into y equals, and then do second calculate and calculate all your values. Or once you put the function into y equals on your calculation screen, where you do all the work on the calculator, you can select the vars menu for variables and go to function and select y1 or whichever y you put the function into, and then calculate each of them, and that'll allow you to do it pretty quickly. Okay, so let's try this from the right. If we're doing this from the right, the picture looks a little different. And we're using the endpoints 1/2 to 4. So now we don't use the 0. But the the rectangles are still the function times delta x. Okay, but now we're going to start at a half. Okay, so we've already calculated most of these in the previous example. So we also need to calculate the f of 4. And then again, to get the final area, we just add them all together. Now notice the two results are a little different. One is bigger than the other. So let's take a look at why. Look back at our left endpoints. On our left endpoints, every rectangle is a little too large, right? And so this is an overestimate. Now the reason being is because the function is f is decreasing and concave down. So that puts the left endpoints going a little bit above the curve. Okay? In the right endpoints example, we notice that they're all a little too small. So this is an underestimate. Okay, and the reason for that is because it is, again, decreasing and concave down. Okay, so this would be what we would call a lower area for 8 subintervals. Okay, the left endpoints, so this would mean lower in our notation, and if they say u of 8, they're doing the upper, so you would just coordinate those with either left or right, depending on whether the function is decreasing or increasing, to figure out which one's bigger. Okay, so take a little time, maybe play with this same function, but do it with 6 subintervals or 10 subintervals. Of course, the more rectangles we use, the more precise our estimate gets. Okay. Next time we will look at using midpoints, and we'll actually play around with using trapezoids a little bit. So we'll see you then.